Welcome everyone into Chapter 8, where we are going to start learning about right angle trigonometry. So for some people this is sort of familiar. This is using sines and cosines and tangents in the context of right triangles. So just in this section what we want to do is discuss how trigonometric functions are related to right triangles, learn about complementary angles, and then solve what are called right triangles. So if you have a right triangle where you have some information given, can you solve it, aka can you complete it, find all the angles and all the sides? And then there are some applications. So in our unit circle definition, okay, if I put an angle in quadrant 1, okay, so now theta is in between 0 and pi over 2. Okay, it could actually be 0, but it won't be equal to pi over 2. Then the coordinates of this point are given by cosine of theta, comma sine of theta. And what that means is, if I were to draw this triangle, we would have theta here. We'd have a hypotenuse of 1, because it's the radius of the circle. Our height would be sine of theta, and our width would be cos of theta. But now observe this triangle that's drawn over on the right, okay? It has a right angle. Our triangle had a right angle. It has the angle theta. Ours has the angle theta, which means this angle here is the same. So the three angles between the triangles are identical, which means the triangles are similar. So this means that corresponding ratios are the same. So for example, letting this be the angle theta, I'm going to describe this side as opposite that angle and this side as adjacent to that angle. This I don't call a side, it's the hypotenuse. It's across from the right angle, it's the hypotenuse. So when you talk about the side adjacent to an angle, you mean the not hypotenuse side adjacent to the angle. Okay. All right. So ratios of sides will be the same between these two triangles. So for example, the ratio of the opposite side over the hypotenuse. In the blue triangle on the right, that is b over c. It is opposite of theta over the hypotenuse. But now let's look at the red triangle over here. Opposite is sine theta, and the hypotenuse is 1. So sine theta over 1 will be equal to b over c, because these two triangles are similar. And if you set up all the other ratios you can, okay, the adjacent side to the hypotenuse in the blue triangle is a over c, but in our original triangle, it's cosine theta over 1. Etc., etc., etc. Okay, so you get all of these things here. Really, it's the top row that you're going to want to pay attention to. Sine theta is opposite over hypotenuse. Cos theta is adjacent over hypotenuse. Tan theta is opposite over adjacent. Okay, the other ones are just reciprocals of them. This is commonly remembered as SOHCAHTOA. Sine is opposite over hypotenuse. So there's your SOH. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. This is a common mnemonic to remember exactly how it works. What I do want to emphasize again, though, is this has to be a right triangle. Okay? If you have a triangle that is not a right triangle, actually that looks kind of like a right angle. If you have a triangle that's not a right triangle, then this doesn't apply. Okay, we'll see there are ways to study triangles that are not right triangles, but for now, SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. That only applies to right triangles. So find the value of each of the 6 trigonometric functions, aka sine, cosine, tangent, cosecant, secant, and cotangent, of the angle theta. So what's missing is that opposite side. So how am I going to find the length of that opposite side? Hey, we're in a right triangle, so use the Pythagorean Theorem. Okay, the sums of the squares of the two sides are equal to the sum of this to the square of the hypotenuse. So 5 squared plus the unknown side is 13 squared. This is going to give us that the unknown side is of length 12. So now we can fill in this triangle as having side lengths 5, 12, and 13. So what will the sine of theta be? So remember your mnemonic. SOHCAHTOA. So sine is opposite over hypotenuse. What's opposite theta is 12. What's the hypotenuse? 13. So the sine is 12 over 13. The cosine is 5 over 13. The tangent is 12 over 5, and so forth for the cosecant, the secant, and the cotangent. Okay, so just review this, make sure that you can understand these various ratios. I want to mention something else about this picture, so I'm going to erase my marks. So I could have called this angle here, let's call it alpha. Now, alpha is an angle in a right triangle, so I can ask, what is the sine of alpha? Sine in a right triangle is opposite over hypotenuse. But 12 was opposite theta. What's opposite alpha is 5. So opposite over hypotenuse. So a lot of people get really hung up on the orientation of the triangle. Okay? Because when it tends to be written in books, almost always the triangle is oriented like this and the angle theta is put on the left. They get really used to thinking this is the opposite side, this is the adjacent side. But what really matters is what angle you're talking about. Okay? So if we were talking about this angle, then yes, 12 is opposite. But if I change color to mark it, let's go with green. If I'm talking about this angle, then this is actually the adjacent angle, and this is the opposite angle, side length, sorry. Then 12 is the adjacent side, and 5 is the opposite side. So don't get too fixated on how the triangle is oriented. Okay? As long as it has a right angle, any of the angles in there, you can talk about opposite versus adjacent. Now, there's definitely a relation. I mean, these are not totally unrelated to one another. So back to red. And let me clear off all of my ink. So what do the angles of a triangle add up to? If you said 180, I hope you said degrees. We're going to work in radians, okay? So if I call this angle alpha, first of all, this angle, this right angle in radians is pi over 2. So what that means is theta plus pi over 2 plus alpha, if I add up all three angles, must be pi, which is the angle of a triangle, 180 degrees. Subtract pi over 2 from both sides. We get theta plus alpha is pi over 2, which means alpha is pi over 2 minus theta. Okay? So then, if I was to take, for example, the cosine of alpha, on the one hand, what's the cosine of alpha? It's going to be adjacent over hypotenuse. If alpha is the angle, then 12 is adjacent. So the cosine of alpha is 12 over 13, right here. But I could also say the cosine of alpha is the cosine of pi over 2 minus theta. And one of the identities we established back in chapter 7 is that the cosine of pi over 2 minus theta is actually the sine of theta, which we already knew was 12 over 13. So there's a relationship between the sines and cosines of different angles in the same triangle. The sine of this angle is the cosine of this one. The cosine of this alpha is the sine of theta. The tangent of alpha is the cotangent of theta. Okay? Here is actually why they are called cosine, because the angles theta and alpha complement each other in this way. Again, I'm clearing out my marks just so it's a little cleaner. The sine of theta is the cosine of alpha. The sine of alpha is the cosine of theta. The tangent of theta is the cotangent of alpha. Okay. The secant of theta is the cosecant of alpha. It works for those as well. Okay, so point here, don't get fixated on a particular orientation. As long as you're in a right triangle, what you're really keeping track of is what's opposite, what's adjacent, and what's the hypotenuse. A common error is to mistake the adjacent side for the hypotenuse. But remember, the hypotenuse is the one across from the right angle. The adjacent is the non-hypotenuse side next to the angle. Okay, so this is a problem that we've looked at before. And honestly, the way it's presented here is exactly the way we did it back in chapter 6. Okay. If I make a rain gutter 4 inches long, divide it into thirds, so 4 inches, 4 inches, 4 inches, and I angle these two things up the same amount. I make an angle of theta in both of these sides. I now have a cross-sectional area that represents how much water can flow through the gutter. And the formula for this area is given right down here. Okay? So back in chapter 6, the problem was find the area for theta equals 30 degrees, 45 degrees, and 60 degrees. And we're quickly going to go through this. This is exactly how we did it back in chapter 6. So first, you just plug in 30 degrees. Sine of 30 degrees is 1/2. Cosine of 30 degrees is √3/2, which is approximately 14.93. For 45 degrees, both sine and cosine, both sine and cosine are going to be √2/2. That simplifies just down to about 19.3. And for 60 degrees, finally, I know I'm going through this quickly, but we have done it before. Sine of 60 is √3/2, and cosine of 60 is 1/2. So we plug those in, and we get a final answer of about 20.7. Okay. So great, we can compute the area of various angles, but where did this formula come from? So let's take a look at this diagram, okay? So this length is 4. I need to know what this height is, because then I can find the area of this rectangle. And I need to know what this width is, because then I can find the area of this triangle, which is the same as this triangle right here. Okay. So the triangle on the left has a right angle. This is 4 inches. This is h, whatever the height of the corresponding gutter will be. And then you can observe what we have is we have like ground level and the top of the gutter. And this is cut by that piece of the gutter there, which means these two angles are congruent. They are opposite, adjacent, what's the term? Opposite interior angles. I forget the term, but when you cut across two parallel lines with a third line, it creates a pair of congruent angles. So down here, this angle is theta, which means this angle here is also theta. And then on the right-hand side, observe we have a right angle, we have a length 4, we have a height of h, and this angle is also theta. So these two triangles, the left and right one, are congruent. So my total area is going to be the rectangle plus 2 times the triangle. Okay. Now the rectangle is of area 4 times the height. The triangle is of area 1/2 width times height. And this 2 and that 2 cancel off. So I have 4 times the height plus the width times the height. Okay. I'll just go ahead and factor an h out, 4 plus width. So the question becomes, can I determine the height of the rectangle, aka also the height of the triangles, and the width of the triangles? So let me get rid of a couple of these pen marks, not all of it. Okay, so let's take a look at that triangle. So here is an enlarged version of the triangle. I guess it's not really that enlarged. Let's start setting up some trigonometric ratios. Observe it is a right triangle. So if I take the sine of theta and if I take the cosine of theta, what do I get? So sine of theta is going to be opposite over hypotenuse. What's the side opposite theta? H. What's the hypotenuse? 4. Similarly, what's the side adjacent to theta? W, and the hypotenuse is 4. Now, if I just take each of these and multiply them by 4, we get that h is 4 times the sine of theta. And we get that w is 4 times the cosine of theta. Hooray. Now I'm going to plug that in. Okay, so coming back over to the right-hand side, h is 4 sine theta, and w is 4 cosine theta. Now I can factor a 4 out of this second parenthetical term, giving me 16 sine theta 1 plus cosine theta, which was the formula given in this problem. So the real point of this example isn't just to redo the computations we did in chapter 6. It's here is where that formula comes from. It's an application of various triangles. Now there's a handy little shortcut when you're working with triangles. So I'm going to erase everything, so copy down what you want. Okay, so there's a handy thing to remember when it comes to working with triangles. Anytime you have a triangle, if I know the hypotenuse, and I'll call it r, okay, and I have the angle here, okay, call this height, call this width, then the sine of theta is h over r, meaning the height is r times the sine of theta. So similarly, you'll get w, sorry, I guess you'll do cosine of theta is w over r multiplied by r, and you get w is r cosine of theta. So this comes up a lot in Calc 2 and in Calc 3 and a bunch of other courses. Anytime you have a right triangle, if you know the hypotenuse length and you have this angle here, you immediately say opposite is r sine theta and adjacent is r cos theta. What it does is it reduces a right triangle to two pieces of information. What's the hypotenuse length and what's one of the angles other than the right angle? If I know those two things, I can immediately get all three sides. And of course, once I have two angles, I can find out the third. So as long as you know the hypotenuse and a single non-right angle, you can immediately start filling some stuff in. Anyway, that's going to wrap up this first video. Okay, we've defined what sine and cosine, and then therefore tangent and cotangent, all that are in right triangles. And the thing that you want to remember is that mnemonic SOHCAHTOA, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. As long as you're in a right triangle and you can orient what side is opposite what angle, you're golden. Okay, so when we come back in the next video, we're just going to learn about complementary angles, which we already touched on a bit today, but we're going to do some sample problems using them.